Hello, let's start today's class. Today we are going to talk about linear regression, and in this class we are going to talk about two linear regression model. One is simple linear regression model, the other is a multiple linear regression model. We are going to use a Pikachu sim data, which is provided by our class. And in the simple linear regression, we are going to examine the relationship between the Thunderbolt power with the training time. And in the multiple linear regression, and we are going to evaluate multiple factors like training time, data quality, and battle experience, and determine how they are jointly affect the Thunderbolt power. Okay, let's start with simple linear regression. In simple linear regression, this is how a general data may looks like. Okay. In simple linear regression, we aim to determine the relationship between two covariates. Here, for instance, one is training times, the other is Thunderbolt power. So here we examine data, including 10 data points. Then the first row would be our first observation, who have the training time as 1.5 hours, and with corresponding Thunderbolt power as 42 volts. And the second one would be another observation with 2 hours training time, with corresponding Thunderbolt power as 45. And we are, in total, we are going to have 10 such observations. And if we put as a plot and putting Thunderbolt power as the Y or vertical, then training time as horizontal or X, we are going to receive such a scatter plot. As you can see here, with the training time increased, the Thunderbolt power is going to be increased correspondingly. And we suspect that we can find a model that can explain the relationship between the two variables. Okay. By looking at this plot, the most naive guess would be a straight line kind of relation. So in such a way that if we can find appropriate a line that fits the data very well, and we can build the model between the two variables. That motivates us with the simple linear regression model. Again, in the simple linear regression model, we are trying to make the prediction about the one variable using the other. In here, we are going to put Thunderbolt power as the one being predicted and the training time as the one that make the prediction. And conventionally, we use Y as the response variable or dependent variable that we want to predict, and X that's as the explanatory variable or independent variable. Sometimes they be called regressor or predictor. And here, the Y in our example would be Thunderbolt power, and X would be the training time. Again, to predict the response Y for a given value of X, and we assume a linear relationship between Y and X, then the model can be written as Y equal to beta 0 plus beta 1X. Here, the beta 0 would be called intercept, and the beta 1 is the slope. And the beta 1 is used to depict the relationship between Y and X. If beta 1 is positive, that means the X will increase together with Y together. If beta 1 is negative, and they are going to have X increase, Y decrease correspondingly. And if beta 1 is equal to 0, there's no relationship or linear relationship between Y and X. And in general, when we have n observation, and for each kind of n observation, we are going to observe y1, x1, y2, x2 until yn, xn, and the data is going to be organized in the form presented here. And we also know that in the real life, we may have a random fluctuation of the data. That's the reason why we introduce the random error term epsilon, and they are going to be our random term that is going to be appearing in predicting y using x. And since the random error is introduced, then the model can be rewritten as yi equal to beta 0 plus beta 1 xi plus epsilon I. Here, I is the index for the observation, representing the first, second until nth observation. In the simple linear regression model, we do need to assume certain assumption with respect to the epsilon. For instance, the first one would be the expectation of epsilon equal to 0. That means the mean random error should centered at 0. The second one would be the variance of epsilon I equal to sigma square, so that the sigma square is called the random error term. As you can see here, the sigma square does not change from one observation to another. That's why the second assumption is also called homogeneous variance assumption, which means the variants are homogeneous crossing all the observation. The third one would be the epsilon I are independent identical distribution. That means no two observation have going to have the correlated random error. And last one but not the least, to draw inference, we commonly assume epsilon I follow normal distribution with a mean at 0 and variance at sigma square. All those four assumptions are commonly assumed for simple linear regression model so that we can deduce some very useful property for the corresponding estimation. As you can see here, using all the above assumption by checking the expectation of the model, and we are going to find that the epsilon I is equal to 0, and that gave us the epsilon yi equal to beta 0 plus beta 1 xi. And the variance of yi, since they are totally depending on the randomness of epsilon I, so they are going to have the same variance as the epsilon I, who have the variance equal to sigma square. And here we assume that xi are constant, so that if we can determine xi, and we can predict the epsilon expectation of yi. And again, the error variance should be a constant, and beta 0 and beta 1 are unknown parameter that need to be estimated. Then the question is, how do we estimate the parameter beta 0 and beta 1? Okay. So the idea would be simple. Since we assume our linear model observed as yi and xi, so basically that means the true observation shouldn't be deviated from our theoretically assumed model very much. That's the reason why if we define the epsilon I hat as yi minus beta 0 minus beta 1 xi, which is the deviation from the observed yi with the mean model beta 0 plus beta 1 xi, and we want to have the difference or the deviance between the two to be smallest. That's the reason why we define the sum of square or SSE as sum of square of this deviance. And we are trying to minimize this term so that we can get the best beta 0 and beta 1. This method is called method of least square method. In order to obtain the least square estimators for beta 0 and beta 1, we take the partial derivative with respect to beta 0 of the SSE and the partial derivative with respect to beta 1, so that we are going to have the following two equations. And to force those two equations, or the first partial derivative, to be both equal to 0, and we can solve the corresponding minimizer or of the mean square error of some square term, and so that we are going to have the following solution. Okay, the mathematical deduction will be skipped here, and but this is just a simple two unknown and linear equation system. So you should be able to solve for beta 1 hat, and they are equal to the following expression. And by simplify a little bit, we are going to see that they are no different than the ratio of the two. In the denominator, they are xi minus x bar squared, basically sum of the variance from xi to its own mean, or sxx. In the numerator, we are having the cross product of xi minus x bar times yi minus y bar and sum them together, and we denote as sxy. So this would be the minimizer about the SSE mentioned above for beta 1. And we can solve also by the beta 0, and beta 0 is equal to y bar minus beta 1 times s bar. And why do we add a hat onto that? It's just to remind yourself they are just estimators for beta 0 and beta 1. They may not necessarily to be the beta 0 and beta 1. So as you can see here, the y are random variables. So that means when we observe the y from 1 to n, they do have the randomness inside. That's the reason why the beta 1 hat is actually a random variable. So are the beta zeros. Therefore, the fitted or the estimated regression line can be using this expression and with a hat onto the yi. And the yi hat is equal to beta 0 hat plus beta 1 hat and xi. Note there, y hat is only a predicted value for the yi. There's no way they are the same as yi, since the true yi do have the randomness epsilon I there. And also the beta 0 hat and beta 1 hat have no mean to be the same as beta 0 and beta 1. They are just estimations. And therefore, the epsilon I hat we have previously discussed, which is going to be the estimated one as the epsilon I. And this special estimated error is what we called the residuals, okay? So basically what we are going to have is we are going to have the yi minus beta 0 hat minus beta 1 hat and xi sum of square of them to be smallest one, while the beta 0 hat and beta 1 hat are the one that minimize the SSE. So this gives the mathematical justification why the beta 0 hat and beta 1 hat we list there are the least squared estimators. Okay. So geometrically representation about the above mentioned solution is that we are going to find such a blue line so that they are square distance between each of the dots to the data or to the line as what we are plotting here, the square of the distance for each of them. When they sum them together, they are going to be the smallest possible. And this line is what we have as y hat equal to beta 0 hat plus beta 1 hat x. Okay. So this blue line would be the least square line or least square fitted line for the data that can be used to predict the training using using the training time and to predict thunderbolt power. And sometimes we are also interested into estimating the error term or the random error. So the estimation of the error or a bias of it can be written as sum of square of estimation minus and minus 2. This can be proved that they are unbiased estimator for the model error sigma square. And similarly, we can also using what we have in the previously hypothesis testing knowledge to conduct hypothesis testing. And most importantly, to test whether the model hold a certain linear relationship. In particular, for the null hypothesis with beta 1 equal to beta 1 star, while the beta 1 star is hypothetically hypothetically beta 1, and it's going to be distributed as the following formation. As you can see here, we do need the unbiased estimator for sigma square in order to build the corresponding test statistic. And this test statistic is going to follow the t distribution with n-1 degree of freedom. And with this t statistic, we can actually do or conduct hypothesis testing to test whether beta 1 is equal to 0 or not, or put in simply, whether we should assume a linear relationship in the data. And the corresponding confidence interval for beta 1 can be also given here. And we have to note here, again, if you have failed to reject the null hypothesis beta 1 to 0, that implies there's no linear relationship between y and the x, okay? And also, if the null hypothesis of beta 1 to 0 get rejected, then there might be an implication that the linear term in x residence in the model is applying a significant portion of variability in the y. Okay. That also means there's no other relationship other than linear. For example, it might have a second order relationship, but that is out of scope of the linear regression model's discussion. So to summarize, in order to test the null hypothesis, beta 0 equal to beta 0 hat against a suitable alternative hypothesis, and we are going to have the test statistics built in such a way, and the corresponding confidence interval is given as the following, and for beta 0. But since we are not that interested in testing the intercept, so sometimes we are not focused on discussing it. And we just let you know that we do have ability to test whether the intercept is equal to 0 or not, or given a suitable confidence interval for the intercept term. So in order to fit the model, and we are going to use the R to run the fitting model of them. and this would be a typical R commanding for the running the model. Okay, so let's read the commands them line by one. So in this one, in this command means we are going to save the results from the right-hand side to the left-hand side variable called simple underscore model. And in this model, we are going to have a LM represent the linear model, and we are going to use Thunderbolt power as the prediction and the training time as a predictor, and the data here will be the picture data. And this command summary is going to make the summarized result for the simple linear regression model above. And from the output, we find that the estimation for the intercept or beta 0 is equal to 33.61. So this is our beta 0 hat. And the beta 1 hat is equal to 5.7818. And the corresponding t statistic value is equal to 50.04 and 34.56. And they give you the p-value for each of them equal to 2.82 times e to the power of minus 11, which is very small number, okay? That's equivalent to e10 to the power of minus 11. And the same thing for the beta 1. And this one has a p-value equal to 10 to the power of minus 10. So basically that means by any standard of tradition use significance level alpha, and we are going to reject the null hypothesis which claim beta 0 and beta 1 equal to 0. And the estimated model of the original one is going to be the yi hat is equal to 33.6182 plus 5.7818 times xi. And that means with every 1 unit of increased hour of training time, and the corresponding Thunderbolt power is going to increase positively with 5.7817 units. Okay, so this is how do we interpret the model. So in order to measure the quality of the fit of the model, we introduce the following concept, which is called coefficient of determination. Before we understand it, we need to revisit the first concept we have previously introduced, which is sum of square of error, SSE, which is defined as yi minus yi hat, square and summing together. And in the ideal case, or if the model fits perfectly, we know that yi and yi hat should have no difference, which make SSE equal to 0. And the second one is called total sum of square, which is yi minus y bar square and summing together, which represents the variance of the response value that ideally would be explained by the model, or the largest possible total variation that need to be explained from the model. So as the SSE to be 0, that's representing the ideal case, then that's give us the reason why the quantity of the difference between SST and SE, which is written as ST minus SE, is going to be a measurement of quality of the fitting. Or if we are standardize that quantity by or divided by SST, and we are going to have the coefficient of determination R squared representing as 1 minus SSE divided by ST. As you can see here, this quantity is going to ranging from 0 to 1, with 0 as a perfect non-fitting and one as perfect fitting. So from the previous output, we have seen that they are R squared is equal to 0.9933. That is a very high number that is close to 1. That means around 99% of data variation from the Y can be explained by our model that will be listed here, 33.61 plus 5.78 times xi. So the higher the value of R squared is, the better the model fitting is going to be. Okay. So there's a note we need to put here. So firstly is that if the whole model fit perfectly, R squared will be 1. And if the SST minus SE equal to 0, that means there's no fitting in the model, and R squared is going to go to 0. And R squared mirror the amount of variability explained by the model. And the higher the value is, the better the model fitting is. There's an important comment that need to be noted for the R squared, is that R squared criteria is dangerously to use for comparing competing model for the same data. Why? Because adding more terms into the linear model, we are always decrease the sum of square of SSE, so that they are going to increase R squared all the time. Even though the additional regressor does not explain anything or does not explain significantly, they are also get the R squared decrease or SSE, get R squared increase or SSE decrease. That's the reason why we should be very careful by simply using R squared criteria to select the model. But again, the R squared is indeed a common measure for the quality of fit. We want to have R squared to be a large number if the model would be the pre-given or prefixed. Okay. So often the problem of analyzing the quality of estimated regression line is going to handled by analysis of variance. In particular, in order to see how the model can be decomposed or model variation can be decomposed into the one that can be explained by the model we propose with respect to the part that we cannot explain. And we are going to talk about analysis of variance. Basically, how do we explain or analyze the variance of the total? So as you can see here, we have the SST, which is sum of square of the total, is yi minus y bar square, which represents the maximum possible variation that is going to observe from the data. And this term can be decomposed by the two term, and we can do it by minus yi hat plus yi hat. And it can be demonstrated that the yi minus yi hat plus yi hat and y bar, if we treat it as two terms, and we can decompose that as the next line, and with the first term as yi minus yi hat square summed together, and yi hat minus y bar square summing together. And together with the cross product term, with two times I from 1 to n, yi minus yi hat has y hat minus y bar. And in the next slides, we are going to show that the product term here is actually equal to 0. And if this cross product term equal to 0, we can actually finding that the sum of square total can be written as the sum of square of yi minus yi hat and y hat minus y bar. And the first one we already explained is sum of square of error term or sum of square of residual. And the second term, y hat minus y bar, representing the variation that can be explained by our model, while the y height is the prediction from the model. Okay. So in the ideal case, since SST is always keep the constants if the data has already been observed, and we want to have such a model with SSE equal to 0, which means SSR is going to get closer to the SAT. That's the reason why SSR is the sum square due to regression, or it's the amount of a variation in the explains its response that can be explained by the model. The larger the SSR, the better the fitting the model is going to be. Okay. So here we note that the least square estimator beta 0 hat and beta 1 hat is going to satisfy the following true condition, so that it's going to be equivalent to say that yi minus y hat summing together equal to 0 and y minus y hat times xi equal to 0. By using the above property, and we can actually show that the cross product term, as what we have previously deduced in the second line above, is actually equal to 0. So in fact, y minus y hat and y hat minus y bar can be decomposed as the true term as written here. And by projecting in the y hat into the model, and we are going to have the beta 0 hat times the sum of yi minus y hat and beta 1 hat times the sum of yi minus y hat xi. And we already show that since the beta 0 hat and beta 1 hat are our mean square estimator, that imply these two terms, the sum of the yi minus y hat and y minus y hat times xi is going to be 0. That's basically justify why the cross product term equal to the 0. And that's also justify why SST can be decomposed by SSE and SSR. And in order to test the null hypothesis with respect to the slope or the coefficient term for the x, that's equivalent to say we are going to test the beta 1 equal to 0 or beta 1 not equal to 0, we can propose another test statistics called F test statistics. They are SSR divided by 1 divided by SSE divided by n minus 12, which is going to be following F distribution with the first algorithm to be 1 and second algorithm degree of freedom equal to n minus 2. And this quantity happen to be the square of the t statistic we have proposed previously for beta 1 square with n minus 2. And you may wonder, why do we propose the F statistic rather than the T statistics before? It's because this statistic is more generic to test a more generic model when we have a multiple linear term. In the linear regression or simple linear regression, the F and the T square are the same. But that will not be the case for multiple linear regression when you have multiple cohorts that can be introduced in the model. And we are going to have the analysis of variance of table looking like this way. So in general, the first column is going to list the name of the source of data variation. One is due to regression, and the second one due to the random error or residual that can't be explained. And the last one would be the total variation. As what we have already previously discussed, the SSR plus SSE is equal to SST. And with the third column, degree of freedom, which representing the as the t distribution of the term of SSR and the t distribution of SSE. So we also show that SR and SSE, if the data following the normal distribution, and we can show that the SR is going to follow a t distribution with degree of freedom 1, and SSE is going to follow the t distribution with the degree of freedom n minus 2. And by taking the ratio about the mean squared error, which is SSR divided by 1 and SSE divided by n minus 2, sometimes we call this term MSR to represent the mean square error, and this one we call it MSE to represent the mean square, the other one is mean square regression, and second one is mean square error. And from the hypothesis testing, we have previously learned if we have a two t distribution standardized by the corresponding degree of freedom and take the ratio of the two, they must follow the F distribution. And if this F distribution have a large quantity, then that means the SSR is going to have a significantly larger ratio compared with SSE after accounting for the corresponding degree of freedom. That is going to, it means the regression model is going to provide a significant proportion about variation among the total data variation SST. And we can use F-test here to test whether the data is or the simple linear regression model is appropriate, or we can use the t statistic that be previously introduced. Okay. Again, since in simple linear regression, the t statistic corresponding to the f statistics is just having the squared relationship. That's the reason why the test statistics about those two are identical to each other. Okay, let's go back to the previous analysis to take a look. So as you can see here, the beta 1 have the test statistic equal to 30.56 with corresponding p-value equal to 5.37 to the e to the power of 10 to the power of minus 10. And they also list the f statistic value, which is 1194, which is the square of 34.56, of course, with some random rounding error, and with a p-value precisely the same as the one of the t statistic. So basically, the f statistic that's going to be introduced to test the general model variation that can be explained by the regression model are going to be equivalent to be the test statistic that is proposed to test whether the beta 1 should be treated as equal to 0 or not. But again, this is only for simple linear regression. When we talk about multiple linear regression later, and we are going to revisit those two outcomes. So again, this will be the general ANOVA table from the output we have previously observed. As you can see here, the total sum square of the model that can be explained by the model is 689, and the unexplained variation is 4.6, and with the mean squared is 68.689 again, and with the mean square error at 0.57, with corresponding f statistic equal to 1194 and the p-value equal to 5.37. And the code for generating the ANOVA table has been attached here. Okay. Okay. So But as every statistical model, we need to test whether the assumption is going to be fulfilled. Put it in another way, if there are any indication that the assumption that we assume are not fulfilled or there's any violation of them, and the results may not be reliable. Okay, so we are going to have three kinds of assumptions that's going to be tested here. So remember, we do assume that the model error have sigma square as the variance, and sigma square does not changing from the one observation to another. That is what we call homogeneous variance assumption. And also we do assume the data follow the normal distribution. And the second one would be normality assumption. And the last one would be independence of residual assumption, the RID assumption. So let's talk a little bit of all three of them using the following plot. In general, we are going to use the fitted value again or residual against the fitted value to test the assumption 1 and the assumption 3. And we are going to use the normality QQ plot, which is the theoretically the quantile from the residual towards, sorry, the observed residual and with the theoretically normal data. So if they form a line, that means the data may follow normal distribution. Okay, so the first plot, again, when we plot the residual against the fitted value, and they are going to be the one we are going to use to take independent identical assumption and the common variance assumption. As you can see here, so when the data changing from smallest one to largest one. So as you can see here, the data show there's no like pattern or systematic pattern of the data variation, and sometimes they are negative, sometimes they're positive. That means the residual change does not systematically change corresponding to the fitted value. That basically means there's no significant variation or violation of the model assumption 3, which is independent of the residual assumption. And secondly, if you take a look about the variance of the model, okay, basically the variance of the model is going to ranging from minus 1.0 to 0.1.0, of course, subject to some variation. Since we only have a 10 observation, we really cannot think too much observation or violation from this common variation assumption. So basically the data is going to be distributed around 0, no systematically, and with common variance around 1. So yeah, please ignore this auto-generated curve from the R, and so this sometimes it's going to be useful, but in our case, this is not going to be helpful since we do not have that many observations. And so the assumption 1 and 3 are having no obvious violation of them. And let's take a look at the right one. And the right one is standardized residue corresponding to theoretical quantile. So the theoretical quantile is corresponding to the standard normal distribution. So basically what we are going to do is that we are going to rank the data or rank our residual from smallest to largest and plot it one by one with another ranked theoretical quantile from standard normal distribution. So if they are increasing in the same speed or a common speed as straight line, and we are going to assume the data following normal distribution, or the normal distributed assumption for the random error does not get violated. As you can see here, most of the data following a straight line, the only exception would be 5 and 6. And this is maybe due to the no such kind of enough data points in our data set. So that's the reason why from observing of this data, although we do see some indication, but in general, we have no strong evidence to say there's a significant violation about the normality assumption. Okay, so after this graphical detection of the model, and we are going to see that the three assumptions have no obvious violation, even though they have some minor violations, but that can be explained by the lack of data. And we are going to assume the model is still valid, or at least to be useful in make the reliable prediction. Okay, so this part ending for the simple linear regression.